Okay, so as actually, this is number 4, not number 3. Sorry, I should have. Didn't mean to write number 3. This is number 4. All right, remember in the last video we had just figured out what's called the solar constant. It's just the amount of flux arriving from from the sun that is 1 astronomical unit away. Then they say, okay, well, what would be the flux if the sun were 10 parsecs away? By the way, why are they doing 10 parsecs away? Because, of course, 10 parsecs is the distance that we imagine all stars to be that far away when we use the absolute luminosity scale. All right, so 10 parsecs away, this is how you'd mathematically put the stars 10 parsecs away. All right, so anyhow, if the luminosity of the sun, of course, it's how many watts are coming off the surface of the sun. That's 4 times 10 to the 26th. And so, how did I get this number? The 4 pi. Well, that's just the surface area part. But how did I get this 3.09 times 10 to the 17th? And remember, that's the distance of 10 parsecs in meters, and then you have to square it. All right, so you get this number. Now, 1.2 times 10 to the 36th square meters. But so how did we get this? So 10 parsecs. It turns out 1 parsec is 206,264.8 astronomical units. So the parsecs cancel, and then you multiply in 1 astronomical unit. Remember, that's the distance from the Earth to the Sun. There's 1.5 times 10 to the 11th meters. So you multiply, all these numbers together, right? These numbers right here, all right, and this is what you get right here. All right, so that's what the denominator is. All right, and so when you divide the flux at 10 parsecs away that comes from our sun is very, very small. Here, let's make this. So the flux at, that's supposed to be an at symbol, 10 parsecs is going to equal, let's see, I get roughly 3.3 times 10 to the minus 10th, 10 to the minus 10th watts per square meter. Right? Remember, watts are joules per second, so that's the energy per second per square meter. All right, so that is number 4, right? Yes, and now we're going to do number 5. All right, so number 5 says you have 2 stars, A and B, with a luminosity. So here's what we're going to do. So you're going to say the luminosity of star A. They give us what it is. It's 0.5 times the luminosity of our sun. And then the other one, the luminosity of star B, is 4.5 times the luminosity of our sun. All right, so that with that in mind, respectively, are observed to have the same apparent brightness. So when we look up in the sky, we would see both of these stars with the exact same brightness. And the first part of it is pretty simple. Which star is more distant? Okay, so that one you can answer right away, right? If they both have the same brightness, and the luminosity is really the amount of energy that's coming off of the star. The one that would be further away is the one with a smaller luminosity, right? So that's the one that's much further away. Now, how do we figure? And then the much more interesting question says, and how much further away is one than the other, right? So that's the question that we have to answer. All right. So luminosity of A is 0.5. The luminosity of B is 4.5. right? So, and by the way, the main equation that we're going to use is this, the flux equation, right, which we just had. The flux, in general, flux is equal to the luminosity divided by 4 pi, which is just the surface area of a sphere, 4 pi r squared, or where r is the distance from that object. All right, so we're going to use that in this information here to get our number 5, or solve our number 5. So this is how we're going to solve this problem, right? Now, how can we set these two fluxes equal to each other, right? Because that's really what I just did. I just said the flux of A equals the flux of B. Really, that is just written out in equation form right here. The reason that we can write that is because it says number 5, let's see, times respectively, are observed to have the same apparent brightness. So this is why we can write that. The fact that they get the same apparent brightness. Right? So right away, if you have these two equations, the 4 pi cancels, right? So this right here is the equation that we're going to work with. All right, so now we know what we know what L sub A is, and we know what L sub B is, right? LA is 0.5, so it's 0.5 times the luminosity of our sun, and we're going to see the luminosity of the sun cancels in just a moment, divided by the distance to A. All right, so the distance to A squared, and that's going to equal the luminosity of B, which they gave us as 4.5 times the luminosity of the sun, that's a 5, divided by the distance to B squared. Right? And of course the luminosity of the sun, this is sun, the luminosities of the sun cancel, and so this becomes, if we rearrange the equation, just cross multiply the distance d sub A squared comes over here, the d sub B squared comes over there, and so it looks like, let's just do this. So it's going to be the distance. Let's see. It's going to be hold on. So I just cross multiplied, and this is what we come up with. 0.5 times the distance to B squared is equal to 4.5 times the distance to A squared. All right, and then we really want to know what the distance to B is compared to the distance to A. And so let's solve this for the distance to B. So the distance to B is equal to, the 4.5 has to be divided by 5, so it's going to be 4.5 divided by 0.5, divided by 0.5. And then, since the distance to B is squared, I've got to take the square root of that, right? And then, of course, I got to take the square root of the distance to A, but that's squared already, so that's just times the distance to A. And so this becomes the square root of, just take 4.5 divided by 5, and you'll see it's going to be the square root of 9 times the distance to A. And so the B is 3 times the distance to A. So star B, which is, it's three times as far away as star A. And that answers question number 5. All right, so let me make sure I read this. Number 6, a star has an apparent magnitude of 10 and an absolute magnitude of 2.5. So the apparent magnitude, little m, is the apparent magnitude, it's 10, and then the absolute magnitude, capital M, is, what was it, 2.5. 2.5. All right, so the equation that you use for this kind of thing is, it looks complicated, but it's actually pretty simple. So the distance to any star, if you know the absolute magnitude and the apparent magnitude, is the power of 10. So it's 10 raised to this quantity called well, let me just write it out. So it's going to be little m, so the apparent magnitude minus the absolute magnitude plus 5, and then that entire quantity divided by 5. All right, divided by 5. And so that will be the answer. It'll give you some number of parsecs. The answer will be in parsecs. All right, so that's how that works. That's how this works. All right, so here let's set this up. All right, so remember, little m is 10, capital M is 2.5, so it's pretty simple. It's going to be 10 raised to the quantity 10 minus 2.5 plus 5. Remember, you got to do what's in parentheses first, and then divide. That's supposed to be a plus sign, and then that whole thing divided by 5. And so the way I always do this is you do what's here in the parentheses, then divide by 5, and then you take. There's always a function in your calculator that says 10 to the x or something like that. Here, and so let me do that. All right, so I've worked this one out. So the 10 minus what was it? 10 minus 2.5 plus 5 gives you 12.5, and then you divide it by 5, you get 10 to the 2.5. All right, and so you raise 10 to the 2.5 in your calculator, and remember this answer comes out in parsecs, so that's going to equal, and this is the answer for number 6. It's going to be 316. That's a 0.2 roughly. 316.2 parsecs. All right, so that's the distance when one star has an apparent magnitude of 10 and an absolute magnitude of 2.5. That's how you do that. All right, let's set up the next one. It says use the data in figure 17.7 to calculate the greatest distance at which a star like the sun would be seen. A, with binoculars, B, with a 1 meter telescope, C, with a 4 meter telescope, and then D, with the Hubble Space Telescope. So all this table is doing is it tells us what the magnitude of the object would be able. The object. What would be the magnitude of an object if you look the minimum magnitude that you could see, like with a pair of binoculars, or a big telescope or something like that. So here we'll set this up. All right, so here's the equation. It's the exact same equation that we used in number 6. So little m is the apparent magnitude. Capital M would be the absolute magnitude. And so and this is the end of the parentheses, and that whole thing in the parentheses is divided by 5, and then the whole thing you take 10 to whatever the power is. All right, and the answer, of course, is going to be some number of parsecs. All right, so what we have to do, of course, is look up the magnitude, the absolute magnitude, capital M, of the sun, right? So if we look up the absolute magnitude of the sun, it is 4.83. Right, 4.83. All right, so that's the absolute magnitude. Just as a little quick comment, that it's a pretty dim star, right? In the night sky, a star exactly like our sun at 10 parsecs away would, it's visible, but it's not like one of the real bright ones out there at all. All right, so the first one, part A. So let's do part A. That's supposed to be an A, is for a pair of binoculars. And so a pair of binoculars, a really good pair of binoculars, would see down to an apparent magnitude of about 10. That's supposed to be a 10. All right, so the distance that you'd be able to see this would be, well, we just have to set it up. It would be 10 to the 10th minus 4.83 plus 5